So the first thing we did with the Scorpion when we programmed this was actually program the finish operations. In this case, the geometry was so complicated, we found it better to create finish motion and then add the roughing to make the finish motion possible. So we have two setups in this part. We have Op1, where we have the full cylindrical blank mounted to a rock lock base, and then Op2, where we have the bottom finished, we mount it to a custom fixture and stand the part up. The majority of the work happens in Op2, but the tail specifically was split between Op1 and Op2. So we needed to kind of find a method that worked for both sides of the tail that was pretty uniform. In this case, all made possible by the unified multi-axis toolpath and the fact that this was a mesh body. Programming to a mesh actually made this a little bit easier, in my opinion, than if this were a solid body, and I'll show you why. So we can see there are already toolpaths existing in this file. We have one of the Op1 segments done, and this is something we're just going to kind of continue along the other segments. So here's a blank multi-axis toolpath for segment number 3. If I open the parameters, this is just a fully blank unified multi-axis toolpath, so we're starting from scratch here. What I need to first do is select a drive body. So let's select machining geometries here. And I'll open up level 2 where our Op1 drive surfaces live. And you'll see this is actually a trimmed up version of those full segment meshes. We can see here, there's the full mesh. This is just a trimmed kind of a half body of the tail segments. Okay, and the next step is to select a cut pattern. In this case, we'll just go with automatic. What I like to do at this point is basically immediately see a preview of the toolpath. So let's turn on Generate Toolpath and click Apply. And we see a preview of this tool motion. What we're looking for here is that the toolpath structure itself, those blue lines that show the path of the tool, we want to see that looking nice. And in this case, they look pretty good right off the bat. If I were to open this in backplot, we would see this toolpath is far from finished. You know, I can drag the tool along the toolpath here, and we see all sorts of collisions, a lot more motion than what we need. Once we get toward the second half of this body, things clean up pretty nice, but the first half is needing a lot of work. The first thing I want to focus on is limiting the tilt motion that we see here. We can see the tool is tilting really everywhere, but specifically, I don't want this tool to tilt toward the left at all here. I want to draw a 45-degree line here and keep the tool to the right side of it. So if I go to our tool axis control page, I can turn on limits. In this case, if I just apply a limit in the XZ plane, so notice the X direction and the Z direction, I want to let my tool go from 0 degrees, which is 3 o'clock, to 45 degrees, so 45 degrees from that 0, and let's just click OK. With that toolpath regenerated, we can backplot once more, and we can see this motion looks much, much better. In fact, the tool is always in a safe place, except for when it's violating the neighboring tail segments. And this is where making this on a mesh really helped us out, because each of these bodies is an individual body that we can use for collision control. So let's activate some collision checking. On the collision control tab, I want to check my flutes against the neighboring bodies. So we'll turn on avoidance geometry and select the full bodies. So let's turn off level 2, select this and this. I want to trim those collisions out completely. Say OK. And we'll see a lot of retracts maybe now, but we now know that tool is safely not colliding with the neighboring tail segments. There is still one problem though. Because we created this toolpath against a small version of that tail, if I run Analyze Toolpath and show somewhere around here, we actually see that there is a sizable gouge into the tail body here. And that's because we never told Mastercam that this full tail body exists. Right now, Mastercam thinks it is safely missing the drive surface, when actually it's gouging the real body. So what I need to do here is add one more level of collision checking. In this case, it's just going to be a simple flute-only retract tool against the full body here. with no stock to leave. If I say OK. So now with that generated, if I open Analyze Toolpath once more, I can zoom into that same point and see that we are no longer gouging against the full tail segment. From this point, there's just some standard multi-axis cleanup work to do. Clean up the retracts, clean up some of the links. So if I open the parameters, I can add some final multi-axis cleanup items. For example, I changed my clearance area to a sphere with a radius of 4 inches. I tightened up my retract distances just to kind of cut down on some wasted motion. I added lead-ins and lead-outs to the first and last move. And I got rid of the blend spline just to keep the motion a little bit tighter. I also want to make my lead-in and lead-out move a little bit smaller than what the default values are. And now if I click OK, we can see what our final result is. So we have something that's nice and tight to the part. All the retracts are nice and safe. And as I run this through backplot, we have a really good multi-axis toolpath to finish this side of the tail. So that's the first side of the tail done. Now in the second setup, we flip the part over and come back with a unified multi-axis toolpath, except this time we ended up using a clean core method to finish this part. If you're not familiar with what the clean core method is, it's the use of a clean surface body as your drive surface and collision checking against the actual bodies. So let's open up Op4. Same thing, this is a unified toolpath that's completely blank. We need to select our machining geometry. That machining geometry lives on level 4. This is the nice clean core surface we created. And in this case, we actually used the guide curve method. So let's select 1 and then 2. And again, let's just preview this before we do anything else. And we can see the motion that we get is some nice linear motion that follows the flow of the tail lengthwise. However, it's only directed to the surface rather than to the tail itself. Let's run this through backplot so we can see the tool motion. We can see the tool starts out at 90 degrees relative to the vertical and is always staying normal to the surface. You can see there's a lot of motion here. We don't really need the tool to be doing so much tilting. So in this case, let's add another limit to our multi-axis tool axis control. Except this time, let's go with the conical limit. Because we're on a trunnion style machine, this conical limit will serve as a B-axis tilt limit. So anytime this B-axis moves, I want to tell it never tilt more than 45 degrees. Let's say OK and check this out in backplot. Now this tool is staying locked at 45 degrees of B tilt, and then the C-axis will spin around. We never let it stand up more than 45 degrees, and the same thing on the other side. So we really cut down a lot of wasted motion just by adding a tool axis limit. Of course, this is not a finished toolpath by any means because we're not actually machining the surfaces that we're targeting. So let's turn off the level with the clean core surface and turn on the level with the drive surfaces. In this case, we're going to use collision control to drop the tool onto these surfaces. So we're going to be working on the blue part here. So let's open up the parameters, and under collision control, we want to use the flute to retract the tool to a specific avoidance geometry. If I say OK and preview this, nothing's going to change because there are never any collisions with this body. What we need to do is come down here and activate drop down tool. If we turn that on, the tool will drop down along its axis anytime it will possibly contact this surface. However, that leaves all this area out here of wasted motion that's not actually machining anything. So what we can do in this case is remove the areas where the tool drop fails. And now we're left with a really nice trimmed up toolpath. Again, made possible by the fact that this is a mesh body. We trimmed up that mesh body, which actually worked as a containment boundary for this multi-axis toolpath. We can see, however, there are still collisions with the neighboring segments. So let's go back into collision control one more time and just do a simple flute where we trim and relink to the neighboring full tail segments. We don't want to collide with this one, and we don't want to collide with that one. If we preview that, we'll see the toolpath trims up nicely. But again, we only drove the tool to the trimmed version of this segment. So we need to add one more collision check that says retract the tool away from this full body because we will have some collisions down here. Say OK. We should see that this area kind of lifts up a little bit. And now we have no collisions with our drive surface or with our neighboring tail segments. There's only one retract at the very end of this toolpath, so there's really nothing to clean up there. And at this point, this is just a matter of repeating the same process for all the tail segments, and that's how we program this entire tail of the Scorpion.